From here to the stars. I am your host, Stephen Euin Cobb. Our guest today is Sarah Lamm. Sarah Lamm is a PhD student researching biosignature potential in opals for application to Mars and future Enceladus missions. She completed her master's degree in 2021 at Kansas State University, focusing on the chemical composition of chlorite minerals using Raman spectroscopy. She has extensive experience with NASA, completing internships at both the Jet Propulsion Laboratory and Los Alamos National Laboratory, where she worked with the ChemCam instrument on the Mars Curiosity rover. Passionate about science communication and outreach, she founded Rocks and Rockets, an annual STEM event in her hometown of Colby, Kansas. She is also preparing to apply for the next round of NASA astronaut applications for the Artemis program. Thank you, Sarah, for taking the time for this interview.
Yeah, thank you so much, Steve. I'm excited to be here.
Excellent, excellent. You earned 3 simultaneous Bachelor of Science degrees in geology, chemistry, and geography. What drew you to these particular fields?
So I went to Kansas State University for my bachelor's, and they don't have like a astronomy program or a planetary program. And I realized that planetary, you just need the fundamental sciences to be able to do planetary. You just need to then take those sciences and apply them. So I thought long and hard about what sciences spoke to me and what would be the most useful. So I really liked chemistry both in high school and I took it at a community college level, and I really liked that. So I was pretty dead set that I was going to do that. Plus, if for some reason I didn't go into planetary or grad school, I was going to go be a lab technician in chemistry because I really enjoyed that kind of stuff. And I thought chemistry really explained well, maybe like the atmosphere of like gassy planets or just atmosphere of any planets. And then to complement that, I did geology. So explain like what's going on the surface, under the surface, and basically how are those rocky planets and or those moons are forming. And then geography, that one was not originally planned. That one came about because I was trying to get some physics classes scheduled for like a minor, but I could never get that physics 3 scheduled. I always had a chemistry class or a geology class on top of it. So I chose to start taking just mapping classes. That way, when we were seeing these planets and anything happening, we could like understand it in the spatial context. So I started taking so many that I figured out that I could just make that into the 3rd degree.
Okay, cool, cool. What were the benefits and especially, I think, the challenges of pursuing 3 bachelor's degrees concurrently?
Um, I think some of the benefits were I was never bored. I was always able to be challenged or keep trying. So that was really fun. I don't do well with being bored. I need something to work on. Um, I think the biggest challenge was actually scheduling because it is just so difficult to make sure like nothing overlaps. So I had to take some classes in kind of strange orders just to make sure that I got all the classes done. So I took, I think, a junior level geology class as a sophomore. I took uh, honors chem 2 and then organic chem 1 at the same time, and usually those are maybe a semester apart. So I really had to both push myself to figure out the scheduling conflicts and prepare ahead of time. But then all of a sudden you were in some really tough classes all at once. So
You spent 3 summers at Los Alamos National Laboratory working with the ChemCam instrument on the Mars Curiosity rover. Your research focused on the distribution of manganese oxides in Gale Crater on Mars. Why is manganese significant in the search for past life on Mars?
yeah, so manganese oxides on Earth, so I'll bring it back to Earth for a moment.
Mhm.
Manganese oxides on Earth really didn't show up in high abundance until we have this like great oxidation event because you need both water and high oxidizing conditions to even produce them. So we assumed prior to Curiosity that there's going to be like a few manganese oxides, but not in abundance. And then they started finding them in like 10%, 20%, 40% weight on Mars. And they're like, that shouldn't be possible. Like Mars's atmosphere, to our knowledge, did not like never had that much oxygen. And they've realized based on not just manganese oxides, but other things that, oh, Mars's atmosphere did have more oxygen. So it starts asking all these questions for both habitability, but also like what do we know about past Mars? And turns out not as much as we thought we did.
Hmm.
So they had already made the discovery before I showed up. So my job was to start tracking it, like when we started spiking again and when we started like going down.
You presented your findings at conferences and contributed to scientific publications. What were the key discoveries of your work?
I think the key discovery of the work was showing like how the lake kind of had stood still for a while, just so it had to have that like oxygen exchange with the atmosphere. So I
Hmm.
think finding like a lot more understanding that original lake was probably the most important.
Have they verified absolutely that Gale Crater once had a lake in it?
Yes, that they actually knew before we ever landed. So, since Mars just has so many orbiters going around it and taking pictures, we could see from orbit that there were like geological signs that water used to be present, both in terms of like, rivers running inside of it, like geomorphical things, but also we had certain orbiters that could like look at the mineralogy, at least from a distance, and was like, this is very consistent with water and or specifically lake minerals.
Okay, cool. Your research involved analyzing data, creating manganese pellets for calibration and participating in rover operations. Can you describe a typical day during your time at Los Alamos National Laboratory?
Yeah, so I would say there was kind of two typical days. There was the lab work, which you just said, the pellets. So Los Alamos National Lab is a nuclear lab, so it's actually very high security. I think I was actually one of the minorities where I did not have like security clearance. I was an unsecured or unclassified worker.
Mhm.
So all of our lab work though is like behind the gates. So I had to always go like show my badge and drive through and then show my badge again at another security checkpoint and to get to this building that where they've allotted us lab space. So you would then go to the very basement to like the back room and usually no one was there so I could play music and I would just like grind manganese powder together and then measure out the correct amounts and all take all of that and then put it in a hydraulic press so it's really really tight. So that's making these manganese pellets that you mentioned, and that way we know how much manganese is in this exact sample. And then when someone takes it to the laser and shoots it, we can then compare one to one, be like, okay, so we know that there was 50% manganese in this pellet, and that looks like what we see on Mars, or it doesn't. So that was like redoing the calibration.
Hmm.
Um, that actually did not I did not have that much lab work at Lanel, usually speaking. Usually what would happen is I would go to work, I would download the data from the day before, run the calibration we had at the time over it, and it would tell me like how much manganese have we seen today, or at least in the past couple days. And then I would input this all into this giant spreadsheet I had that had like all of the targets, their location, their manganese content, as well as their like silica, calcium, iron, titanium, any major elements. So that way I could kind of see like, okay, is manganese and silica going up together at the same time? They're not. And I would just do this with all the major elements. And that's part of the reason we know it was manganese oxide as opposed to another type of mineral, is because there was nothing else increasing or decreasing the same as manganese itself.
You wrote blog posts about your experience. What was the public's reaction to your work, especially after being featured in Gizmodo and CNET?
Um, so generally speaking, those blog posts don't get that much interest, but that one I know you're referring to, that
Mhm.
one was a very special one or a fun one. So to back up a little, our operation schedules go out, I think at least a month in advance, if not a couple months in advance. And for that month, Curiosity had went down because the computer was not saving any data we were taking. Like the technical instruments were working, but we couldn't save the data, and therefore we couldn't transfer it back to Earth. And that was really an issue for obvious reasons. You don't need to just go shoot things and not have data.
Mhm.
So they shut it down and basically were to release the scientists all from their operations duties while the engineers got to work figuring out like how are we going to fix this. But because they put the operations out so far in advance, when they started getting Curiosity working again, they told the team internally, I think maybe for a day or two, they're like, okay, just so you know, like you can't release this to the public, but we are starting to get this maybe working again. And then whatever day that was, the uh, principal scientist of Curiosity sends out an email, I think, to the blogger team, and it's like, hey, whoever's scheduled for today, we need you to write the update that Curiosity is going to be back on board. And I honestly didn't want to do it because I was like, that's a lot of stress. Like, I'm still in grad school. I was maybe 22. Like, that's too much responsibility. Problem was the schedule was set and it was me. No one picked me. I just got lucky.
Okay.
So, and the way a blog post normally works is you write it, you pick a picture of the day, you send it to the whole team, and then someone from NASA JPL like checks off that you've not like your work like you are accurate and you've not released any information you have not like you weren't supposed to release. Because sometimes there's like a few internal things we're not supposed to talk about. Um, so but this blog post, because of like how special of nature it was, since Curiosity was down for a week, they literally said it like my blog post will go directly to the principal scientist and then he will send it to NASA headquarters. We're not even going to like the JPL press people. We are going straight to headquarters. And no one else on the team were allowed to be on these emails. It was a good thing I didn't have classes or anything else to do that day because there was just constant emails back and forth between everyone of just like I think the principal scientist added one sentence to my whole blog. Other than that, everything else was mine. But headquarters tried to tell him that his sentence was inaccurate, but they didn't know it was his, so they were telling me it was inaccurate. I was like, I'm not like I didn't write that. So they're all going back and forth of if it's accurate, if it's worth releasing to the public, should they word it a different way, all over the single sentence I had nothing to do with. Um, and it did take like a full day. And then I think it took maybe a day or two afterwards for it to actually be published on the website. And then that's when the real fun started with Gizmodo, CNET, and there were a couple other places that started picking it up. So,
Sounds
yeah.
exciting, but also a bit stressful.
Yeah. I was like, at least I can be the one to be like, I got to announce Curiosity was back after a month delay.
Yeah, that's cool. Yeah.
Yeah.
Let's see. Your master's thesis at Kansas State University focused on using Raman spectroscopy to determine the chemical composition of chlorite minerals. For those in our audience who may not be familiar, can you describe what chlorite minerals are and why they're important in planetary science and astrobiology?
Sure. So chloride is a silicate mineral, and it also always forms with water. So that's great for habitability. But what's cool about chloride is it can have different concentrations of iron or magnesium or aluminum based on just where it formed and what temperatures it formed under. So if you have a chlorite mineral on Mars and you want to figure out like what temperatures did it form at, you would take the magnesium and the iron concentrations and use someone else's calculations to figure that out. But the problem is, how do you know it's chlorite and how do you do that? So I had to use an instrument that's already on Mars. So I chose Raman spectroscopy just because that tells you what mineral you're dealing with. And then from there, I created the calibration. I was like, okay, so we know we're dealing with this chlorite mineral group, but I was able to like tease out information. I was like, okay, this is what the spectra looks like when it's more iron rich, and this is what it looks like when it's more magnesium rich.
Your research focused on chloride as a potential geothermometer. Can you explain how this works and it's significant for understanding planetary environments?
Yeah, so not all minerals can be geothermometers, at least not as easily. But as I was saying with the element composition, if you know chlorite's element composition, that's all you need, more or less, for it to be like a geothermometer. So that just tells you about past formations. And as I kind of said earlier, like there are a lot of things about Mars we don't know. So if we have chlorite exposed at the surface, we might be able to figure out a little bit more of like what's going on beneath Mars, or at least under the surface.
A standard room thermometer for, a household, it's accurate probably within a degree or two. What kind of range is this geothermometer as far as it's at like 10 degrees or 20?
I honestly don't know, but because we're also doing it from a distance, you're going to have a lot more air stacked up. So I think my error for my calibration just with a laboratory Raman, which is going to have so much higher spectral resolution, I think for iron was like 3%, but the Ramans on Mars have, bigger error bar. And
Mhm.
then so you are all of a sudden having a bigger error bar on the iron content, and then you put it into uh, the geothermometer equation, that's going to have another set of error bars. So I'm not entirely sure.
Okay, but the fact that you can use it to determine past temperatures is pretty impressive. Uh,
Yeah, at least give you a range or an idea.
yeah, yeah. Let's see. You developed 18 equations to quantify the chemical composition of chlorite using Raman spectroscopy. What challenges did you encounter during this process, and what were the key findings?
Oh, what were the challenges? I think part of the challenges was I just didn't know where to start, like how to do this. So I I've gotten a lot better now and faster, but I would manually what's called curve fitting. So there's like maybe a band in the Raman region, and I was like, okay, is that one band? Is that like actually like made up of three bands? And trying to figure that out, like how many bands is this? And then uh also trying to figure out like what do these bands correlate to? How do you do that?
Mhm.
So I think those were the biggest challenges. Um, I think what was, I think some of the biggest outcomes maybe weren't the equations themselves, but figuring out like, okay, these bands do exist, and they are mostly associated with maybe like the iron and manganese, or not manganese, sorry, the iron and magnesium, while these are almost always associated with like silica and aluminum. So being able to figure out like which bands are connected to what. So if anyone wants to update my calibration later, or maybe do a better job with the silicon aluminum, they already have starting places of they're like, okay, these bands are the ones we have to focus on.
What implications does your research have for current and future Mars rover missions, especially those equipped with Raman instruments? It sounds like you've just described the beginnings of that, but are there any others that I'm not thinking of?
Um, yeah, I think those, at least for my masters, that's the main one, is that we are really starting to test the boundaries of ramen. So that is standard for like mineralogy, but when you start adding like this chemical portion to it, you're really starting to get this powerful instrument that can do a lot more than just tell you what mineral you're looking at.
Okay. Is it possible to take these measurements from a great distance, say from orbit, or do you really have to be close
Oh,
to the sample?
orbit's too far for ramen. You have to be much closer to that. I think Kim Cam says that they can do it from about 20 meters or something, which is pretty far. I would like to see some of the data from that. Because at least the ones I do, it's the micro ramen. So you were like right up next to it. You were shooting the laser through an optical like piece.
Ah, okay.
Um, so that's a lot similar to what Sherlock does. So Sherlock gets right up close and personal, like next to the samples to do it.
I mean, it's based on light scattering, so if you're scattering widely, you've got to be close to catch it all.
Right.
Yeah,
So.
yeah. Your current PhD research at the University of Kansas is investigating the biosignature potential of opaline silica with applications to the Mars sample return mission and potential future Enceladus missions. Why is opaline silica considered a prime target for astrobiology?
So I think it's a prime target for a couple different reasons. Number one, always go back to the water. Opal forms in water. So that's great. The other thing is opal is not a true mineral. So minerals have crystalline structure. It's very rigid. Opal, on the other hand, it's like these silica colloidals or like little balls, and they just like plop down. So they are really good at capturing fossils. And we know this from like Earth-based studies that opal can do this. So I think opal would be great because it's so hard when it does solidify that for the most part, you're not going to just break it off. Even I think it should be durable enough to travel like from Mars to Earth or from anywhere. So if you collect it, it might have contained fossils. It should be durable enough to travel, but also, at least on Mars, this is an issue. They keep talking about looking at like clay minerals for, fossils, biosignatures, and that's very realistic on Earth. But when you're dealing with clay minerals on the surface of Mars, you have to also consider all of the ultraviolet radiation that is like penetrating it and breaking down those original chemical signatures. While opal is actually UV resistance, I think under like 2 centimeters or something. So it could be right up at the surface and you collect it and send it back. So I think for those reasons, opal's a very good candidate for this in the future, or at least for maybe more original biosignatures. Clay would still be good, but you might not be getting original biosignatures. And
Okay.
trying to figure out what the original chemical molecule was based on what the altered is not trivial.
Okay.
So, yeah.
A few years ago, I interviewed someone who was a specialist in meteorites, and a popular place on Earth to collect meteorites is Antarctica because they're dark and the snow is white. And so, plus, they accumulate because the snow melts periodically, and you end up with a layer that's just loaded with meteorites. And some of them are from Mars. Would opal be able to protect the material inside these meteorites that have been blasted from Mars and re-entered the Earth's atmosphere?
I think it would depend on how like big they were. And also if the opal was like on the inside versus like the edges.
Hmm.
I would think if it was on the inside, it probably could, because at that point I'm not as concerned with maybe the impact as much as like, okay, so now you're on Antarctica with all this water flowing in. I'd be worried about maybe like the erosion
Hmm.
or the weathering.
Yeah, right. Your research involves comparing biogenic and inorganic opal from the Ogallala Formation in Kansas. How can this help distinguish between opaline silica deposits that formed through biological processes versus non-biological processes?
Yeah, so what we're doing there is we are basically looking for um differences in the Raman shift or in the Raman spectra. So sort of how I was looking for the differences in chlorite between like iron rich and magnesium rich, we are looking for any shifts that we can attribute to biological. So if it shifts one way or another, or if a band appears, but only in the biological systems, but not in the inorganic ones, then we can start to figure out like, okay, this is what we need to look for.
How might your findings influence the selection of landing sites and sampling strategies for future missions to Mars and icy moons like Enceladus?
So I've not actually been involved with any of the landing site stuff. I kind of know how it works, but I think I need to actually like prove my results before they'll actually take me seriously.
Okay.
And then after I have my results, anyways, I plan to go back with the Perseverance data set and then run it on that and be like, okay, so with my calibration, this is what we would have seen on like Perseverance. And then I think from there I could make a good point and be like, we need to go somewhere that has opal. Even though opal, I've read, is actually pretty widespread on Mars for the most part, it's not that uncommon. So like Gale Crater has it. Jezero Crater, they're pretty sure has it already. Uh, I mean, Gusev Crater, so where Spirit landed, it does. I think Opportunity saw not a ton, but I think saw a little. And then definitely Sojourner. But at the time there wasn't enough scientific instruments for them to confirm that. But there was really high silica for what they would like they thought they saw for the region. And they were thinking what happened was the silica coating kind of came over these basalt rocks. So when you take the, bulk chemical measurement, it says you have a lot more silica, but and that would be true, but the still basis is basalt. You just had silica coated. So
Okay.
silica is pretty widespread. Um, so I'm not sure, even if like we prove I have the best method in the world, I don't know how much I would have to fight for a landing site because silica is just so common on Mars.
Silica's common on Mars. Have we done a lot of Raman spectroscopy on Mars? Is there a lot of back data that you can go through and check?
So, so we Raman only first appeared on Perseverance, so both Sherlock and then also Supercam. So I'm not sure that Supercam has a lot of data, but I know but Sherlock does. But the issue with Sherlock is that it's a deep UV Raman, which is great for organics, but they cut off part of the spectral region. So the one that I would need the most for like opal identification, but also seeing how mature the opal is, that's all cut off. So
Okay.
it will, yeah, it'll be a challenge. It's not impossible. There are ways to use the Sherlock stuff for me. And then I'll just have to see what Supercam like actually has. So,
During your internship at NASA's Jet Propulsion Laboratory, you worked with machine learning to identify iron minerals. Describe why iron minerals are important for in the search for life beyond Earth.
okay, so this is talking more about maybe prebiotic chemistry. So a lot of the stuff I've done talks about more like, preservation of these alleged fossils. So iron is interesting because when it's heated up in water, it can have these like create these electron gradients. And there are studies that suggest that iron minerals might be the beginnings of life. So because they can create these kind of gradients, uh, like carbon molecules can start like accumulating and start growing bigger and bigger. And we've seen this done on Earth at what's called a hydrothermal vent, where these iron minerals are being produced in this hot environment, all this water, and these carbon molecules begin to accumulate and form like these complex molecules. So the whole thought is iron minerals are the key to life. So if you go to an ocean world, you will not get all your data back. It is too far away to talk to in real time. Mars, we don't even get data in real time. We can't. It's far enough away, but we will theoretically get all the data back we've ever taken because it's A, close enough, and B, we have enough orbiters that can just keep sending things as we go. Once you start getting past Mars, that data latency becomes a real issue. You are going to have to use machine learning. You are going to have to pick and choose, like, what do you send back? Um, so if you get to Enceladus and you actually somehow get inside of it, like underneath the icy crust and like down into this ocean, if you start seeing minerals, you're not going to know that till at minimum probably an hour later, probably more. I don't remember the rates off the top of my head. But your robot can't just sit around in icy water for an hour just waiting for you to do something after it's done one thing. So, the machine learning part will help it decide, like, okay, we see pyrite, we send that data back. We see quartz, we don't care. Or maybe we'll like send a note, but we won't send like the full spectra. And basically, it's going to help make those kind of decisions of like, what does it do next and what does it send back?
Okay. So the farther away, the because of the light delay of the travel they signal, the more important the machine learning will, for it to make decisions locally.
Yeah. And I
Okay.
mean, yeah, like Perseverance, I don't think has that much machine learning built into it. And I'm not talking about like when the data sent back and people use machine learning there. But I was like, I don't think Perseverance itself has that much. I know it had some when it was landing, And I also know that there's like it's called Aegis, and SuperCam uses it to like pick targets. But Perseverance being on Mars, you don't necessarily need it as much, other than there's times where you don't want it sitting around, and we haven't like scheduled operations for it.
Mm-hmm.
But that kind of thinking goes out the window once you get too much further out. You are going to have a lot of this designed and have your robot making decisions.
That was Sarah Lamm. This has been From Here to the Stars, a video series created by the Interstellar Research Group. The IRG is a non-profit organization dedicated to thoroughly exploring the science and engineering that can eventually open up the reality of interstellar travel. Join us October 12 to 15, 2025 in Austin, Texas for the Interstellar Research Group's 9th Interstellar Symposium. Learn more at irg.space. I have been your host, Stephen Euin Cobb. If you enjoyed this video, please hit the like button, and you can subscribe to our channel for other such videos. On behalf of all of us here at the Interstellar Research Group, I thank you.